Okay, so we're going to keep going with probability. And now we're going to look at probability distributions and the expectations we can expect. So what is a probability function? A probability function maps the possible values of x against their respective probabilities. So what we're saying is if we're talking about a coin flip, the probability of getting a tail would be 0.5. The probability of getting a head would be 0.5. So that would be the probability distribution function. It must be a value between 0 and 1. We talked about that. 0, no chance of occurring. 1 will always occur. Could be those, most likely it'll fall between those two numbers. And the area must be equal to 1. So if I add up all the probabilities, it has to add up to 1. So here's one example of a graph. If we were looking at a dice roll, this would be a uniform distribution. Each roll has a 1 in 6 chance of occurring. If you add up all the possibilities, the 1/6 plus 1/6 6 times, you'll end up with 1. So in this case, this is an example of a probability distribution graph for rolling one die. And this would be the table that goes along with it. The probability that I roll a 1 is 1 out of 6. Probability I roll a 2 is 1 out of 6, and so on and so forth. Notice that they still add up to 1. That makes this a probability function. This is a uniform distribution, meaning they all show up the exact same amount of times. They all have the exact same probability of success. This does not have to happen this way. So let's look at an example. The question is this a distribution function? Well, we look at the probability. The probability that I'll get a 9 is 0.23. Probability I get a 10 is 0.20. An 11 is 0.30. And a 12 is 0.27. Well, I have to ask myself two questions here. The first question is, do they add up to 1? The second question is, are they all values between 0 and 1? In this particular case, they do add up to 1. So yes, it is a probability function. Here's another example. In this particular problem, now I have the numbers 1, 2, 3, and 4 as my random numbers. And I look at the probability distribution on the other side, and there's one issue down the bottom. These do add up to 1. So they do cover the very first criteria. But the problem we run into is that we can't have negative probabilities, because our probabilities must be between 0 and 1. So this is not a probability function. And our third example, if I have the random variables 0, 1, 2, and 3 with this breakdown, no negatives, the problem is that they do not add up to 1. Okay? If you add these all together, you're going to end up with a value that's slightly bigger than 1. So this is not a probability function. The key with your probability functions is they have to add up to 1. There can't be any negative numbers. So if you were given a table and one of these numbers was missing, and you knew that it was a probability function, you could easily find that value by seeing how much is left where all the probabilities together would add up to 1. So we're talking about 1,000 students here, and each person is to pick a number 1 through 10 randomly. Well, the probability of picking any number is 1 out of 10. Assume that they're actually picking the number randomly. How many students do you think are going to pick the number 9? Well, the probability here of picking 9 would be 1 out of 10, or 0.1. If there's 1,000 students, you would just simply multiply 1,000 times 0.1, and in that case you'd end up with 100. You'd expect 100 students to pick the number 9, along with every other number. What percentage of your students do you expect to pick a number less than or equal to 6? Well, we know that we'd expect 100 students to pick 1, because the probability is 0.1. We expect 100 students to pick 2, 100 students to pick 3, and so on and so forth. So since we're looking at the numbers from 1 up to 6, we would expect 600 students of the 1,000 to pick a number that's equal to or less than 6. That's all based on my probability distribution. So let's look at expected value. So if we're looking at this table right here, this is a probability distribution. The 0.4, the 0.2, the 0.2, the 0.1, and the 0.1 all add up to 1. Well, the question is, What is my expected value here? All I'm going to do is I'm going to take the value, in this case the 10, and multiply it by the probability that will occur, 0.4. I'm going to take the 11 and multiply it by the probability of occurring, 0.2, and I'm going to follow that all the way down the line. So my expected value here is 11.3. Obviously that number does not show up in my table. That's how much I expected to get over the long run per time. If I was picking these numbers out of a bag and I added them all up, I would expect my average outcome per pool to be 11.3. Or in this case, we're talking about ship arrivals per day. When we talk about expected value, it's good decision making. Let's look at a lottery example here. So we're talking about pick 3 lottery. For a pick 3 lottery, you pick 3 numbers, 0 to 9, and they can be duplicated. It costs $1 to play, and if you win about $200 after taxes. Let's say it's exactly $200 you win. We want to find out, if you played a lottery once, how much should you expect to win or lose? Again, we know that if you play it once, there's only 2 possibilities. You lose $1 or you win. Keep in mind that you've played $1. If they then turn around and give you $200, you've only won $199 because you've already paid out $1. But we're talking about in the long run here. How much can you expect? What is your expected winnings or losings? So there's 1,000 possibilities. 10 for the first number, 10 for the second number, 10 for the third number. Only one of those is a win, so the probability that you win is 0.001, or 1 out of 1,000. So I set up my probability distribution. Well, 99 times out of 1,000 I lose $1. 1 time out of 1,000 I win $199. Now I'm going to use those numbers to find my expected value. Since the probability of winning is 0.001, multiply that by 199 because that's how much I would win if I did win. The probability of losing is 0.999 times the -1 because that's how much my ticket costs me. If I multiply those and then add, I'm going to lose 80 cents per dollar per game. So every time I play the lottery, I can't lose 80 cents on one game. We know that. I can only lose $1 or gain 199. But in the long haul, I'm going to lose 80 cents per game. This is how the lottery makes their money. This is how the lottery builds its jackpot. This is also how casinos work, and we'll look at that in 1 second. So now we have this stuff about standard error, or standard expected value. If we take a C value, which is a constant number, and we multiply the expected value by that number, then that's how we're going to figure out what the expected loss or gain would be. So an example, if a casino charges $10 per game instead of $1, then the casino is going to make 10 times as much. So if we know that they gain 15 cents per game if you play $1, if you play $10, they're going to gain 15 cents times 10, or $1.50. If we look down the bottom, let's say we played a lottery. And in this particular lottery, we're going to lose 86 cents. Well, if I play it twice, then I'm going to lose 86 cents both times. So I add those together, I'm going to lose $1.72. Let's go back to our example. So if you purchase 2 tickets on one day, different numbers, what's the probability, or how much should you expect to win or lose? Well, we expect to lose 80 cents on the first ticket. We expect to lose 80 cents on the second ticket. So I'd expect to lose $1.60. What if I play every single day in November? There's 30 days in November. On average, I'm going to lose 80 cents per day. So I would expect to lose $24 in the month of November. Again, these numbers can't happen. We know that. This is what I should expect to happen in the long haul. Again, this is how casinos base their money. And let's look at one example of a casino. So we have a roulette wheel. In roulette, you have 38 pieces on there, and 18 of them are black, 18 are red, 2 of them are green. Well, if you win, if you put your money on red and it wins, they pay you 1 to 1. So if you put down $1, you get your dollar back and they give you another dollar. The problem is it's not a 50-50 split. You only win on 18 out of 38 pieces, and you lose on 20 out of 38 pieces. So my expected value is a loss of 5.3 cents for every dollar. So basically, the casino is going to gain about 5 cents per game if I only play $1. Now, the casino is looking at this through the long haul. They're looking at this as thousands of people play every single day. They're going to win some cases. People are going to win. The casino's got to pay out money. But slowly but surely, they're going to win 5 cents per game for every dollar. If you play $10, they win 5 times 10, 50 cents per game. If you play $100, they win $5 per game. And the casino is always going to win in the long run. And there's our example right there if you play $10. Maybe you play 1,000 games, 10,000 games. Again, not just you. This is all the people in the casino. The casino made $5,300 that night on average.